Hi, my name is Simon Guiroy. In this video, I will illustrate the results of our paper towards an unsupervised method for model selection in fewshot learning. It is presented at the Lifelong Learning Workshop of ICML 2020. In this work, we propose a novel method for model selection in fewshot learning. That is, choosing when to stop meta-training before fine-tuning to a new task in order to maximize the generalization performance to that task, avoiding meta-overfitting, which results in a suboptimal solution. Our method doesn't require information on the labels. More importantly, our method doesn't rely on extra validation classes, which allows us to incorporate those classes in the meta-training split and to achieve better generalization to new tasks compared to the standard procedure where we need a meta-validation split to perform model selection. In standard supervised learning, to maximize generalization to a set of test examples, model selection is traditionally performed by keeping a portion of the available data as a validation set, while the rest is used to train the model. In fewshot learning, the aim is not to generalize to a set of test examples, but rather to a new unseen task using very few examples to adapt our model to it. Typically, meta-learning algorithms for fewshot classification use two disjoint sets of classes to constitute the many tasks of the meta-training and meta-validation phases before fine-tuning the model to a test task, which is made of new, previously unseen classes. Model selection is thus performed by selecting the epoch over the course of learning where the model reaches the highest average generalization to the tasks of the meta-validation split. However, this approach to model selection for meta-learning has some limitations. First, we need to keep away from the meta-training split a set of classes for meta-validation, which prevents us from using them to learn more general features. Also, there may be significant differences in input distribution between the meta-validation tasks and the meta-test tasks, potentially resulting in suboptimal model selection. It also requires labeled data, which is in practice more costly to obtain than unlabeled data. In previous work, we empirically studied the objective landscapes of gradient-based meta-learning to better understand generalization in this context. We focused our analyses on the mammal algorithm, as well as its first-order approximation. We notably showed that when adapting to new tasks, a model will generalize better on average when the adaptations to those tasks are more similar to each other. This similarity is measured by the average inner product between the gradient vectors of those adaptations to new tasks. Here in this work, to shed light on the observed relation between coherence of meta-test gradient vectors and generalization, we studied the space of representation that is gradually learned by the model as meta-training progresses. We characterized the global similarity among the representation vectors of the inputs of the test distribution by measuring their average inner product, and this irrespective of their class labels and before fine-tuning the model. This global similarity empirically correlates to how well the model will generalize to new tasks after fine-tuning. Here the intuition is that meta-training would learn a representation space in which the embeddings of the new, previously unseen examples will gradually appear more similar to each other according to their inner product. Thus, the model gradually learns good general features which are able to represent new input samples more similarly. But as meta-overfitting occurs, those features become too specific to the training classes and thus become less general with respect to the new examples, and the similarity between their representations decreases. Using this result, our proposed method is to select, for a given meta-test task, the epoch of highest average inner product between the representation vectors of the few support samples of the task. We measure this quantity before fine-tuning the model to the task. To evaluate the performance of our approach, we use the standard method of model selection via meta-validation as a baseline for comparison. Here we first provide some qualitative evaluations of our method on the mini ImageNet dataset, with results suggesting that our metric reflects the target accuracy of meta-test tasks. We then compare our approach to the baseline, where our method only has access to the meta-training classes, while the baseline has access in addition to the meta-validation classes, which represents 25% more classes in the case of mini ImageNet. Despite this sizable gap between the number of available classes that both methods respectively have access to, our method achieves comparable performance to that of the baseline. But now, when we compare our method to the baseline when both have access to the same number of classes before meta test time, we observe that our method achieves better generalization to new tasks, outperforming the baseline. In this work, we propose a novel approach to model selection in fewshot meta-learning. Our metric doesn't need label information, is computed before fine-tuning, and helps maximizing generalization on an individual task basis, which is what we care about. Finally, it allows to use all available data and classes to train the model. Of course, we plan on conducting additional experiments to further validate our approach, testing it on more fewshot settings, datasets, and meta-learning algorithms. Moreover, in future work we will investigate the effectiveness of our method in the case where there is an important difference between the input distribution of the meta-training and meta-validation tasks and that of the meta-test tasks, and where the advantage of our method over the baseline approach of meta-validation might be even greater.